What's up, party people? All right. So let's go ahead. This is gonna be modern physics chapter 1, which is basically going to be just a review of some classical physics. So now suppose we have a particle of mass m. Moving along with a velocity of v. Has to be. Now, if your particle is with a mass m, moving on with a particle with a velocity that has a velocity v, that means it has a kinetic energy. So that means it has kinetic energy, which is defined as 1/2 mv squared, or a lot of times you like mv squared over 2. Where your kinetic energy, you have a particle that's moving with mass m with a velocity v, having those two components, you have a kinetic energy, and then we would have something called the linear momentum, which is defined as your mass times your velocity. Now, if we remember, so basically your kinetic energy, you know what, I'm just gonna go ahead, just enter. Which is your mv squared over 2. But your momentum is your mass times your velocity. So this is going to equal your momentum multiplied by v divided by 2. Well, if we multiply both the upper and the bottom with your mass, what are we going to have? You're going to have, again, let me just go ahead and get a color. Your mass times your velocity, again, that's your momentum. So basically, you get your momentum squared over 2m. So your kinetic energy is your momentum over 2m. Now, so that's when the particle is moving. Now, when you have a particle collision, so when one particle collides with another, there's two fundamentals that has to be applied. Two fundamental laws applied, which is your first one is your conservation of energy, which is basically your energy before is going to go to your is going to equal to your energy after. Number 2, your conservation of momentum or linear momentum. Which is same thing, your momentum before is going to equal to your momentum after. Now notice for momentum, by the way, let me go ahead and write this down. For momentum, I use the letter rho. Okay, just to distinguish between F and P for pressure. So usually you want to go in a line, have it one open on top. That's your linear momentum. So you got a particle that has a mass, that has a velocity, that does a kinetic energy from your mass and velocity, that has a linear momentum. And when one particle collides with another, two fundamental laws apply, which is the conservation of energy, which is the energy before equals the energy after, and your conservation of linear momentum, which is your momentum before is going to equal to your momentum after. Well, having this, we're going to be talking about, we get the force, which is defined as minus du over dt. Now, this is the force for one, write this down, for one dimension motion. So your force for a one dimension motion is going to equal minus du over dt. Now, what is u? U, that's your potential energy. Now, most of the time, you'll see me write down PE, but your book uses also U for potential energy. So we're going to be using U for potential energy. So your force equals minus du over dt. Your total energy that's associated with it is going to equal to all your kinetic energy plus your potential energy. Now, all right, that's good. Well, so let's say we take our particle that's moving. When a particle is moving with a linear momentum, and again, we're just going to rho at a displacement r. Let me just write this down. At a displacement r from the origin. You get something called the angular momentum, which is given by as L. So basically, let's say your x-axis, this is your y, this is your z. And let's say you got a particle. Let's say this particle is right over here. And let me just go ahead. This is particle of mass m. Now, this particle of mass m, how far is it from the axis? Well, it's going to be the radius going in. If you actually looked at it and it's going in, it's actually the radius. So your radius, that's going to be your displacement, your R. So this is going to be your displacement. And it's going in with a linear momentum rho. Now, your angular momentum is going to equal to your displacement cross your linear momentum, which is basically, you get a different color, you get this one cross this one. So this is going to be your L, which is going to be your R cross your rho. 1, 2, it goes up. All right. So we talked about a particle that is moving, that has a kinetic energy, that has a momentum. When you have a displacement, when you have a displacement, you're going to have your angular momentum. So when you have a charge, this charge is actually emitting an electric field. Let's just say EF or electric field. Now this electric field that's emitted is going to equal to, and it's going to go get the E, 1 over 4 pi epsilon naught, the absolute value of Q over R. Now what is Q? Q, that is your charge of that particle that's on there, the little charge that we have. R, that's your radius between the charge. So the force, so let's say you have two charges. So let's say you have a charge right now over here. You get a charge right now over here. The distance between them from the origin to origin of both of the charges, that's going to be your R. Actually, let me start with this. Yeah. That's R. And they're gonna initiate a force on both of them. Now this force is gonna equal to 1 over 4 pi epsilon naught, the first absolute value of the first charge times the absolute value of the second charge divided by R squared. Now, we've mentioned 1 over 4 pi epsilon naught. Let me just mention this for a second. Let's just take this little fellow over here. 1 over 4 pi epsilon naught. So, we already know what's pi. And epsilon naught, that's a constant. Your constant, which equals to epsilon naught is going to be your permittivity. Let me go ahead and write this down. Just as a reminder, permittivity and free space. Which is going to be 8.85 times the -12. And I think the units is m to the -3rd, kilogram to the -1, seconds to the 4th, grams to squared. regardless, with that constant, having it in 4 pi epsilon naught, that's going to equal to your 8.99 times 10 to the 9th power Newton meter square per Coulomb square. Now, your potential energy, which is, again, I'm going to go with your book as U, is going to be 1 over 4 pi epsilon naught Q1, Q2 over R squared. Again, the first charge times the second charge between the both charges that we have. Now, when that charge moves through a potential difference, delta V, which is basically your voltage, then the potential energy is going to equal to delta U is going to equal to that charge, delta V. Now, again, let me go ahead and label these. Q, that's your charge. V, that's your voltage. And delta U, that's again your potential energy. So, for example, let's say you have a charge of the electron. Let me just say, let's say you have an electron or a proton, they're going to be the same charge. Let's say you have an electron that has a charge of 1.602 times 10 negative 19 coulombs. That's going through a potential voltage of 1 volt. That means your potential energy, which is your Q delta V, is going to equal to your 1.602 times 10 negative 19 times 1, which is going to equal again to 1.602 times 10 negative 19. Now, what is the units that we're dealing with? And now, again, your charge, that's going to be in coulombs. So I'm just going to write that. And this is going to be in voltage, in volts, right? Now, your potential energy is energy. So the units for it is going to be what? Joules, which is always, write this better. Joules, which is the unit of energy. So because we're talking about potential energy, the unit has to be joules. So your result on this, your charge times your voltage, that's gonna get us our joules. So it'd be 1.6202 times 10 negative 19 joules. And that's where we actually talk about the electron volt. EV, which is the energy of a charge equal in magnitude to the electron charge that passes through a potential difference, which is your volts. So basically, your electron volts is the energy of a charge equal in magnitude to the electron charge that passes through the potential difference that passes through the voltage. So basically, your 1 electron volt is going to equal to 1.602 times 10 to the negative 19 joules. And that would be your conversion factor from electron volts to joules. Now, when you're saying, why are we using electron volts? Why don't we just keep it with joules? Well, when you're actually talking about atoms and particles, low charge particles, you're talking about 10 to the negative 8 to the negative 9 with a potential difference in kinetic energy that low. So in order to hide the mass, we use electron volts. So let me actually write this down. The reason is to avoid dealing with very small numbers. So we're going to be doing a lot of work. We're going to be talking about how much it is. It's going to be in electron volts. And we're talking about KeV is going to be 10 to the 3 electron volts. MEV is going to be 10 to the 6 electron volts. GeV is 10 to the 9 electron volts. Which is your giga electron volts. So for example, let's say you have 2 charges. Going in. Your potential energy, which will be defined as 1 over 4 pi epsilon naught E squared over R. The charge of both particles, the first one, the second one, divided by R. And now we're talking about atomic level. And when you talk about atomic level, you're talking about nanometers. So let's say they are separated. We're going to be saying that they are separated by 1 nanometer, which is actually your typical atomic dimension. So basically, our potential energy for those 2 charges that we have is going to equal to E squared over 4 pi epsilon naught times 1 over R. Well, let's take this little fella right now over here. Your E squared over 4 pi epsilon naught. Now, we said 1 over 4 pi epsilon naught is going to be equal to 8.99 times 10 to the 9th newtons meter squared per Coulomb squared. Yeah. Times, so this is your first one, times the electron charge squared, which is going to be your 0.602 times 10 negative 19 coulombs squared. Well, you're going to have a Coulomb square over here that's going to cancel up with that Coulomb square over there. And if you actually plugged it in, we should get 2.307 times 10 to the negative 28 Newton meter squared. All right. Well, what's the Newton meter square? Well, if you actually look at this, let me actually get a different color. If you actually look at, let's look at the unit for a second. In Newton meter square. This is going to be in Newton meters. Now, when you have I guess, yeah. When you have a Newton times a meter, right? And Newton is your unit for force. Meters, that's your unit of your distance, which is your energy or your work. So your energy is your force times your distance. So technically, your Newton meter square is going to be equal to your joules multiplied by your meter. Let me just write this down. Joules. It's for color the way you see it. That's your meters. So basically, this is going to equal to 12.307 times 10 to the negative 28 Newton meter square times, well, I'm sorry, I'm not going to use Newton meter square. And she's going to convert it to joules meter. We want to convert it to electron volts. And we said that 1 electron volt is 1.602 times 10 to the 19, negative 19 joules. Now, looking at this, the units, your joules cancel out. So what you're going to have, electron volts times meter. But then we're talking about atomic level. We have to go to nanometers. So we're going to multiply this by, for every 1 meter, as 10 to the 9th nanometers. And that way, actually, just, 1 nanometers, 10 to the 9th, sorry. 1 meter, 10 to the 9th nanometers. That way our meters will cancel with meters. What you're gonna have nanometers. And your answer will be 1.44 electron volts nanometers. So your E squared over your 4 pi epsilon naught is going to be 1.44 electron volts nanometers. Which is called your electric constant. So let me go ahead and label that out. .44 electrovolts nanometers. Now, if you actually convert it to femtometers, let me go ahead and get black. It'd be sorry, 1.44 MeV femtometer. But basically, the mu we're going to be using the most is 1.44 electron volts nanometer. So that means your potential energy, which is 1 over 4 pi epsilon naught E squared over R, is going to equal to, so we said E squared over 4 pi epsilon naught is 1.44 electron volts nanometers. You're going to multiply that by 1 over R, which is 1 over, we define R as the radius diameter of 1 nanometer. Which basically cancels out our meters, and you will get a potential difference of 1.44 electron volts. Now, wonderful. Now, when you have an electric current running through from those charges, an electric current formed from those charges, which I'm going to give it the letter I. A magnetic field, when you have a current, electric current that you have, so let's say you get an electric current going in I, what's going to happen? A magnetic field, which we're going to call B, beta, is going to be induced or produced. So when you have an electric field I, a magnetic field is produced. This magnetic field again is given with the letter beta or B. Now it was defined as Ui over 2R. Now the magnetic field unit has a unit. The unit for it, so let's say magnetic field. Unit is Tesla, and you give it a big T. Now, Just a reminder, what's a Tesla? It's in newtons per amp meter. Now, so your magnetic field equals mu I over 2R. But what is mu? Mu, or actually it's mu naught. Mu naught is your magnetic constant. Mu naught, which is going to be your 4 pi times 10 to the negative 7 newtons second square over coulombs squared. Now, your magnetic field, you got a magnetic field that creates, and then it creates something called your magnetic momentum. Mu naught, mu. Now, your mu is going to equal to your I multiplied by A. Now, your I, again, is your current. And A, that's your area. So you got a current going in that produces a magnetic field. We already talked about electric field. Produces a magnetic field, and you have a magnetic moment, which is your mu, which is your current multiplied by your area. Now the torque on the loop, down. And we give the torque, I'm going to give it tau. That's what we go with it. On the loop is going to equal to that magnetic moment let's write this down better. Moments. The magnetic moment cross your magnetic field, where your potential energy is minus mu, not cross, it's a dot product, so dot beta squared. And that should conclude chapter 1, what we need for chapter 1 to go ahead for the Krane book for the modern physics. Right now, we're going to be going into a little bit into chapter 2. If you have any questions, make sure to email me or text me or call me or get in touch with me so we can go ahead and set everything up. Thank you so much.